This is the Naica mine in Mexico. For many decades it has been an important source of silver and lead, as well as a treasure trove of geological wonders in the form of giant crystals. Caves below ground discovered during exploratory mining have revealed hidden worlds which appear as if straight out of a science fiction film. Crystals meters long and perfectly formed dwarf the sub-centimeter grains most geologists are used to. It was the discovery in 2000 of a new cave, named the Cave of Crystals, that surprised even geologists used to seeing giant crystals. This cave hosted spectrally large gypsum crystals up to 11 meters long and 1 meter thick. To put this in perspective, a rock consisting of minerals up to 1 centimeter long is considered to be unusually coarse. What processes could have created such fantastic mineral forms, and how does this prove ideas of a 6,000-year-old Earth? First, let's examine the geology of the area. The mines consist almost entirely of layers of limestone overlying layers of evaporites. This sedimentary sequence is indicative of a warm, shallow coastal marine environment which was prone to drying out, depositing salts to form evaporites. Increases in sea level would have prevented drying of the ground and instead led to the formation of limestone deposits. This is the paleo-environment that the geological evidence of Naica mine supports. Following this depositional sequence, the rocks were intruded by hot magma. This magma heated both the surrounding rocks and the groundwater cycling through them. A consequence of this was that the salt minerals in the sedimentary layers dissolved into the hot water, creating highly concentrated hydrothermal fluids. As these fluids ascended to the surface, they cooled and began to deposit new ore minerals which are found all over the area. This is the process by which many ore deposits are formed throughout the world. So why did some of the minerals grow so large? There are several important factors: temperature, a continuous supply of element-rich fluid, and time. Crystals form when a hot fluid cools to the temperature at which a particular solid composition is stable, a temperature termed the liquidus temperature. The number and size of the crystals that form is dictated by the time in which the fluid cools and the amount that it cools below the liquidus. If the fluid is cooled a great deal very rapidly, the result is lots of little crystals. That's why chefs such as Heston Blumenthal make ice cream using liquid nitrogen. The liquid nitrogen cools the mixture much quicker than simply putting it in a freezer, resulting in much finer ice crystals and thus a much smoother texture. If the fluid is cooled to just below the liquidus temperature very slowly, then very few crystals will grow, but they will grow to much larger sizes. This process is dictated by the laws of thermodynamics and is termed undercooling. As the minerals at Naica mine formed, some of the surrounding fluid got trapped in the crystal structure, forming what is termed fluid inclusions. Analyses of these fluid inclusions from along the entire length of the giant crystals at Naica mine revealed that the fluid was held at a remarkably constant temperature of just below 58 degrees centigrade. This is the minimum temperature needed for gypsum to form, and it persisted for the entire duration of crystal growth. Given what we know about how crystals grow through direct observation, laboratory experiments, and thermodynamic calculations, we can use the temperature and size of the crystals to determine how long they took to grow. The answer is on the order of 1 million years, far longer than the 6,000 years that young Earth creationists believe the Earth has existed for. Certainly, there are absolutely no mechanisms of mineral formation known that could produce such huge crystal growth from fluid of the composition and temperature measured in these crystals in such a small amount of time.